Welcome students, this is our video for section 3.1 part A. This whole section deals with graphing linear equations, and in this part of the series we're going to talk briefly about what it means to be linear and how we can recognize something as a linear or nonlinear function. So at the end of this video, you should be able to determine if a function is linear or nonlinear by examining the three following things: the graph of the function, the equation of the function, and finally the table of the function. I want you to be able to look at any of these three things and tell me with a little bit of calculation, in some cases you won't even need that, if it's linear or not. So first thing we'll look at is the graph, and you can tell if a function is a graph by looking at the shape. Alright, if the shape of the graph is not a straight line, then that graph is linear. If the graph is a straight line, then the graph is linear. Okay, linear comes from the word line, so if you see a straight line, it's linear. Now, I use the term straight line for the last time here, because in math, all lines are straight. Okay, we do not have curvy lines or wiggly lines or anything like that. If we have a line, it is straight. So you do not have to say straight line. It is a line. All lines are straight. If it's not straight, it's not a line. Okay, I stress that as a way that we're going to be communicating. Okay, so as we move on, keep that in mind. Now, we're going to go over to Desmos here to see some examples. So excuse me while I click over. Here we are in Desmos, and the types of problems you'll be asked here are pretty straightforward. You see this red line, or I almost called it a line. This red curve, you'll notice, is not a line. Okay, it's not straight, so therefore it's not a line. This one is also not a line. You'll notice it goes up and then down and then kind of shoots back up. Not a line. There. These two dudes, not lines. Okay, but guess what? This one here in green is a line. Okay, straight line, just like you'd expect to see. This is a line. And since the graph forms a line, we can call this function linear. Linear means it makes a line on the graph. So we look at the graph, we see a line, we know the function to be linear. Moving pretty quickly, so take a moment here if you need to pause, rewind, go over this again, and then follow the instructions that come up here in the break. Part 2, the equation. How are we going to look at the equation of a function and determine if the function is linear? In a nutshell, so long as there is nothing fancy happening to x, and I put fancy in quotations for a reason, we'll know the equation is linear. Okay, I put it in quotations because fancy is obviously not a mathematical term, but it does kind of get our point across. Nothing fancy happens to x, we know the equations are going to be linear. I define fancy as anything you could do in the 4th grade or earlier. Okay, so addition, subtraction, multiplication, division. Anything weirder than that's going on with x, it's probably not linear, but if you could have done it in the 4th grade, it's probably linear. Let's look at some examples. Y equals x. I look at x, nothing fancy is happening to x, it's just x, it's linear. But y equals x squared, we didn't do exponents in the 4th grade, x is something funky, x is fancy, that's not going to be considered linear. Y equals 3x plus 6. I look at just the x, 3 times x. We did multiplication in the 4th grade. That's not fancy. That one's linear. But 3xy, we did not multiply x by a variable. We didn't know what variables were in the 4th grade. So that's fancy. That's not going to be linear. 3x minus 7y equals 14. I did plenty of multiplication with numbers, just like we had 3x up here, we have 3x here. It's all good, nothing wrong, we call it linear. Meanwhile, this one's tricky, I have a y squared minus 4 equals x plus 2 now. Nothing fancy is happening to x, but when we graph, we like to have y by itself, so I would get rid of that y squared. Long story short, this is going to end up on x, and it's going to be funky. If you see a y squared, definitely not linear. Keep that in mind. Last, x divided by 4 plus 7 equals y minus 2. Mr. Young, that sure looks like x fourths, and it's the same thing. So this is just division. You could call it a fraction, but you were probably introduced to fractions at that point. Don't get too caught up in it. If you have x over 4, that's linear. But if you have 11 over x, or any other number over x, that's nonlinear. So keep this in mind. Maybe write this down. If you have x in the numerator, linear. X in the denominator, nonlinear. Take a moment if you need it. Finally, we have the table. If the x and y values in the table change at a constant rate, then the function is linear. Let's talk about what that means. If we look at this first example, and this is in your sheet, you can follow along. I look at how x changes. -1, 0, 1, 2. Well, that's +1, +1, +1. Okay? And I will give you a hint. All the problems I have you deal with, x always going to have a constant rate of change. So you will not have to check x every time. But you will have to check y. And if I look at y, I go from 5 to 7, 7 to 9, 9 to 11. That is 5 plus 2 is 7, plus 2 is 9, plus 2 is 11. So every time I change my y value, I'm going up by the same rate. Plus 2, plus 2, plus 2. That means this is linear. Take a moment if you need to. Next example. Again, the x's, I promise they'll always go up by the constant rate, but you have to check y. -6 to -4, plus 2. -4 to -2, plus 2. -2 to 0, plus 2. Each of these goes up by plus 2, constant rate of change. That makes it linear. Now, c, you'll see is different, because now to get from 1 to 3, that's plus 2, but to get from 3 to 7, that's plus 4, and to get from 7 to 15, that's plus 8. So since I'm not adding the same thing over and over again, that's not a constant rate of change, so c is nonlinear. You can mark that in your notes. Take a moment and think about d. Okay, looking at D, we have the same kind of thing, plus 4, plus 4, plus 4 for all the y values, so we can say that D is linear. Okay, now, good news is, that's all there is to this part of the video. We're trying to keep these short, so take a moment, make sure your notes are complete, compare with a partner, and then you should be ready to move on to part B in the series.